Is our first lecture, and you can see mechanical devices can be modeled with the three main elements. There are three main elements. So I would say ideal elements like springs and the damper and the mass. So this is the spring has the stiffness, dampers have damping coefficients, mass, of course it has a body possesses mass. The spring can be modeled with this formula: force equal to K times the deflection in the spring. And if you see the springs, they are in parallel combination. For example, this is a mass, and the mass is hanging from a rigid surface, spring K1 and K2. You can model it as a single element, single spring, which we call as K equivalent. So let me show you the need. If you want to reduce it, the same diagram into one single diagram. So these are the parallel combination. And one thing you will notice that in the parallel combination, the deflection is same for both the springs. Like if we talk about the series, let me show you the difference between series combination or the so in series combination or serial combination, you will see when you apply the force, one spring deflects more than the other spring. But in the parallel combination, the deflection here is same. Suppose if it is x equal to 1 centimeter for K1, so it will be 1 centimeter for K2 as well, because they are in parallel combination. And what will happen in the parallel combination? So if I make a formula here, so in the parallel combination, force is equal to force F1 plus F2. Suppose if I pull um, the total force but due to the spring K1 and K2 is the combined force deflected in spring 1 and spring 2. You have to add both forces together, and once they are added up, so what is the formula for one spring? Any spring has a formula for the linear springs. Right now I'm talking about the linear springs. When you stretch them beyond the linear elastic range, then they become plastic springs, or there are some non-linearity in the springs. So in this case we are talking about the linear springs right now. So I can write down K1x plus K2x, or if I just remove add these two springs together and write down. So compare with this K equivalent. This is the formula. So K equivalent, if you compare equation 1 with equation 2, so X is same for both cases. So this K equivalent becomes equals to K equivalent equals to K1 plus K2. This is true for any uh, parallel combination. Spring stiffnesses are added up. So if you have multiple springs, like more than two springs, one, two, dot, 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 and n springs. So in that case, you will see the spring stiffnesses, they are combined together. The stiffness increases if you see that number of springs are in parallel, you keep on adding parallel combination, the stiffness of the springs, they increase, they add up. Now let me give you a daily life example. So if you think you have um, just a model, a car, so car has like four wheels here, and let me model this car here and here and here. So this spring like here, 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 here. So I can model this as once the car mass is on top of the wheels. So this car, like on the bumpy road or even on the road which has roughness, so the car keeps on oscillating, keeps on moving like a sinusoidal function. Sine wave, you will see sine wave. I just skip one thing, but we call this as x is like sine theta. So this is a simple harmonic motion. So what I'm telling you that the stiffnesses are added up in the parallel combination, and all the wheels, all the suspensions, they are added up into one equivalent springs. This is just the explanation for the hammer. And similarly, you would see that like dampers. So if you have dampers, like if you have uh, they are in parallel combination. So C equivalent will also be added up. The damping coefficients are added up in a parallel combination. How about the series? Let's talk about the series combination. Okay, in the series combination, they become, if there are two springs, they become half. So let me show you over here how do we like in series combination. If I take this, today the lecture will be very light, like introductory or review kind of things. The chapter 1 is not that complex. Even coming chapters, I will try to link it with your undergraduate knowledge so that you should not have any gap. You will be feeling easy for coming chapters. It's not tough. I will try to uh, make it easy to grasp the node. So over here, suppose this node is moving with the displacement x, this node is moving with the displacement y. So if I say that f1 f equals to f1, that is equal to f2, both they are the so in this case, like so I can write down here f1 equals to this is f1, and this is also this is f2. So I want to show you that f1 equals to k times x minus y, which is the difference between the two nodes. Whenever you see a spring, both ends are moving. If both ends are moving, you have to subtract the deflection. Deflection will be the net deflection between the two ends. So x minus y is the net deflection of the spring. And you will see I'm going to derive the equivalent stiffness formula. So F2 equals to, look over here, this end is moving, but this end is grounded. Okay, and if I keep the same formula, like k, this is k1, okay, this is for k1. So if I do the same formula, like y minus other end is not moving, it will be the same k1y. You say k2y. You see my point, guys? So k2y. You see why do I write down k2y? Because the net deflection is y minus 0. The other end is grounded for the spring. Therefore, I just wrote down y2 only. So k2y. And now you will see I can write down a y in terms of f over k2. Can I write down? Because I know that force is same in both springs. And now let's plug it in this equation number one. So can I write on F equals to K1 x minus K1 F over K2? You see my point? I just replace this by this value. It's just plugging in Y equals to F over K2. Agreed? Now I just bring F on the left hand side. Can I write down like this? 1 plus K1 K1 over K2. Agreed? And that is equal to K1 X. So, or F, we need to bring like this. F equals to K1. One thing I want to show you, I want to bring it on the side. Let me do one quick math here. Can I write down like K1, K2 plus K1 or K1 plus, it doesn't matter. It's a sum, so it doesn't matter. So I want to bring uh, this cross multiply, this whole term cross multiply over here. And that will be the K equivalent. Because what is the formula for look at this. The formula for the spring deflection, this is the formula. We want to have this form for any combination. F on the left hand side, K K times X. So I want to bring this everything cross multiply or on the right hand side to have this form like F equals to K equivalent. This will be, if I bring this into this form, then that will be my uh, K equivalent. So can I write down like this? K1 K2 over K1 plus K2. So this is for two springs. And or in other words, I can write down like 1 over K equivalent equals to 1 over K1 plus 1 over K2. How do I write down this into this form? So look over here, can I write down like K1, K2, and K1 plus K2 is just simple LCM and this math. And just flip the both sides. Numerator becomes denominator and then flip that. So can I write down like K equivalent equals to K1, K2 over K1 plus K. And it's the same thing which we just proved earlier. So this is the same thing. So in other words, for the series combination, we have found the formula for two springs. The series combination 1 over K equivalent is equal to 1 over K1 plus 1 over K2. And if you have more than two springs, you will apply the same formula for add 1 over K3, 1 over K4, and so on. Agreed? You understood this point? Okay, that's good. So I can write down the general formula for series combination. And for the dampers, if they are in the series combination, you will see 1 over C equivalent equals to 1 over C1 plus 1 over C2 plus dot 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 1 over Cn. The dampers will have the same um, formula, similar formula. You understanding, guys? Now, as I mentioned, any physical devices or physical any mechanical engineering can devices can be modeled with the help of these three elements: stiff springs, dampers, and the masses. For example, uh, the column, the beams. Like if you have a column, and column is like, this is our top floor, this is our ground floor, and this can be modeled like a spring. Column has stiffness. So you see my point? And so if you have a wheel, a car wheel, so car wheel has the mass and stiffness. So you can assume this is the mass stiffness combination. And if you have struts, like you have struts, and these are the dampers, the coils, and they are attached with the wheels here. So this stiffness of the spring here, and these are the dampers. So C. So the force due to the damper is C times V. C is the damping coefficient and V is the velocity. Sometimes we also write down V as x dot. So you should not get confused that either x dot is the velocity or V is the velocity. It doesn't like matter that way. And sometimes you see torsional in rotational spring, rotational vibration. Let me check some of the students. They might be asking permission to enter the. There are many students who wanted to join. I forgot to add them. But anyways, I'm recording the lecture, so they will have a chance to go home and do the work. So these are the spring I talked about. These are the linear vibration. There is another kind of vibration like a rotational vibration, like a shaft is rotating. Shaft itself, like steel shaft, acts like a torsional spring. Okay, so if you are rotating the shaft, it one end is grounded, so you are trying to rotate the other end, so it will have some deflection, torsional deflection. How would you show me the torsional deflection? So we call this as a torsional stiffness. Suppose if we have a steel column and the disc, this is a steel rod, and the disc is rotating at an angle theta. This is the angular displacement. Over there, the degree of freedom is written by x, which is the linear motion. But in the torsional case, that x is shifted towards angular theta. Now, how would you? There is a. I want to mention there are all the forces. Before I go to the jump to the differential equation of motion, which are very important to find out the natural vibration. I'm taking you towards the end of this chapter, like towards the goal. My goal is that even if you see the column vibrates at its own natural frequency. The car vibrates, any structure, even this table has its own natural frequency. The bridges, they have their own natural frequency, and if you start deflecting those bridges at their structural resonance, then that resonance will increase the amplitude of vibration, which we don't want. We never want any machine to vibrate at the same frequency of resonance, structural frequency, structural resonance, because I'll teach you how to find out the resonance through the mathematical equation. I'll teach you, and that could be a good project for you. You want to design, you want to find out the natural frequency of any structure, and you want to compare with your theoretical frequency, and that could be a good paper later on down the road. So I want to show you, first you should know what is the force. Okay, here in this case we don't call this as a force, we call this as a torque. So K times theta. This K theta, K sub theta means rotational stiffness, torsional stiffness. We don't say that force equal to K times theta. We call it as a torque equals to K times theta. And here K equals to Newton meter per radians. This is the unit. Over there, the unit of the stiffness. Can you guess what is the unit of stiffness in linear springs? Can you guess? Newtons per meter. How about the damping coefficient? Can you guess what is the unit of damping coefficient in linear dampers? Yes, Newton meter per second, Newton second per meter. If you just do the math here, cross multiply here and over here. So if you take a look, the torsional stiffness, torsional dampers, C times theta dot. Theta dot can also be written like angular velocity. Usually we write down angular velocity by omega. You guys understanding? We will do some problems and I will make some more useful videos, like small 5 minutes long or maximum 10 minutes long, so that you can have time to learn the material. Okay, now after we understand these torques, then the next step is to find out the mathematical equation. We call it a differential equation. So we call it as, now we will talk in detail about mathematical modeling of different mechanical system, like mass spring system, like a mass spring damper system, like, because if you understand mass spring damper system, then you can make mathematical model of any structure, either car, aeroplane, a column, or simply supported beam, all these kind of things. Let me share with you another table. I think I can share with you. um, yes, this table. This table is, it will explain you. You don't have to derive this, but you can, this will be useful for maybe for your homework, that what is the stiffness of different kind of uh, structures, like rod in compression tension has a stiffness K equals to EA over L. You see my point? So, and K equals to, for rod in torsion, I mentioned about the rod which is rotating and one end is fixed. How would you find out the torsional stiffness? So this is how they have already derived it. Similarly, helical coil is this formula, cantilever beam is this formula. These are all stiffnesses. Okay, so I want to show you that let's do um, one very quick example of mass spring linear system. I will start from the simple case. Derive the Suppose if you see derive the natural frequency or the DEOM of a mass spring system. So if I ask you this question, what is the derivation math? How would you derive it? So let me show you how would you derive this equation of motion. This X is telling you that this is vibrating in the direction as shown here. Okay, guys. So all the forces, first of all, I would draw the free body diagram of this mass. So this mass I just isolated from the system, and this is my force, I would say minus kx. Now here mg equals to k times static deflection. This delta is static deflection. So when you attach the mass with this spring, the spring stretches with the delta static deflection, and that cancels out the weight effect. So while the mass is oscillating up and down, the weight does not play any role in the displacement or deflection. So how we this deflection plays a role, which is instantaneous deflection or net deflection, subtracting this. So I can model all the forces, they are equals to mass times acceleration. This is Newton's second law. So imagine okay, now here this is negative sign. Negative sign tells me, so in this case if you do the rearrangement, so now the next step, this is our answer. Your answer is complete. You have derived the differential equation of motion for this case, mass spring system. Now I want to find out the natural frequency. So the natural frequency, the standard form. What is the standard form of a mass spring differential equation of motion? So the standard form is this one. Let me rewrite it here. Let me rewrite it over here. X double dot plus omega n square times x. This is the standard form. Some you will compare any equation. Like if you see even a torsional spring, I'll talk about that later on. So if you see, you have to compare this as standard form. So I will say this is my standard form too. So compare. Now our equation one, it is not in the standard form. Why? Look at the coefficient of x double dot. Our equation has the coefficient m, but the standard form says you should have normalized coefficient like 1 for x double dot. So can I do some arrangement? Like if I divide by 1 over m, the whole equation, can I write down like this: x double dot plus k over m times x equals, can I write down like this? Because I want to bring the actual differential equation motion to the standard form. Once I bring it in the standard form, then I know that this is resonance square. This omega n stands for natural frequency. Natural frequency or resonance, they are the same things. So omega n square. What is omega n square if you compare both equations? Can you tell me what is omega n square? K over, good, k over m. So that is the natural frequency square. But we want to get the natural frequency without square. So can I write down? So this is the natural frequency of any mass spring system. You see my point, guys? Now I want to show you how will you find out the natural frequency of a torsional springs. Have you understood this linear spring and mass system? Let's discuss about the differential equation of motion of a torsional spring. So let's take this as a torsional spring. So can I write down, look, derive equation of motion for the rotational case, a rotational motion, where mass is replaced by mass moment of inertia. J is mass moment of inertia. We call it as mass moment of inertia. M is replaced by J, X is replaced by theta, and the force is replaced by torques. I will say torques. Or the moments, they are both same. Sometimes the book write down moments or the torques, so you should not get confused. Okay, torque and moments, I mentioned earlier, it is the turning effect of a force, and that's why we want to turn any spring. So let me show you the shaft. So this is like a shaft here, and now guys, this is rotating. Let me redraw this one a little bit. So I want to show you, this is the, usually this is the way how we show the rotational motion when we apply the torque. So can I write down like this one? So resisting torque is minus k theta. Minus is written, that shows me that it is against the applied torque. Always the shaft will try to resist the applied torque when it is held on one end. So can I write down all the Newton's second law? What in torsional vibration? In torsional vibration, Newton's second law. I would say in torsional. In torsional, as I mentioned, look, force is replaced by torque, and so can I write down all the mass moment of inertia? They are equal to, they are equal to, uh, sorry, all the torques. I'm sorry, there is confusion. All the torques, they are equal to mass moment of inertia times, because in our linear case, all the forces, they are equal to mass times alpha, mass times acceleration. The theta double dot can also be written in some books as like alpha, angular acceleration. So now I'm gonna use this one. Look, this is a free body diagram here. So only one torque is the resistive torque. This is applied torque, J theta double dot. Now here, this is our standard form. I want to show you this one here. This is a torque. So J theta double dot. The standard form is the same but replaced by theta double dot omega n square, either zero or torque. It doesn't matter. I'll explain to you. So kind of write on like j theta double dot plus k theta equals torque, or j divided by j divided by j divided by j. So this is cancelled. So this thing, what is the, can you tell me, looking, compare this equation, suppose equation one with this equation, what is our natural frequency square? K over J. That is the natural frequency. What do you mean by natural frequency? Is resonance. Okay, guys. So I will focus more in the coming chapters about finding the resonance of any structure. And why is it important? We want to reduce the amplitude of vibration so that the structure will not start cracking. Otherwise, structure will start cracking when the, suppose if laundry machine is rotating with the structural resonance of the laundry machine, then there will be some small cracks start fatigue, and crack will start propagating and the machine will start breaking. Now I can take the square root here. I can find out the square root k over j. So that's the end of the lecture. And I want to show you, stop recording.